Hey, good morning, everyone. And thanks for everyone who can make it here in the morning. So make sure that when the others arrive, you tell them, make sure you exaggerate a bit about how good my conference was, so they'll regret not coming. I'd really appreciate it. So my talk, Elixir, well, the screen is, my talk, Elixir FFI with Rust. And I've been talking with quite a few people at the conference here, as one does. And I do realize that both of these programming languages or technologies might be a bit obscure. So I've actually decided to divide my talk into two parts. The first part, I'll just try to explain both Elixir and Rust. And the second part, I'll try to present my project, which tries to integrate them a bit. And as always, make sure you, make sure you interrupt with questions or whatever if there's anything at all. So Elixir, it's a relatively new language. 1.0 was released in 2014, actually. It's a functional language, but not in the pure sense that Haskell is a functional language. It's functional in the way that there's no object-orientedness in it, and you call functions to manipulate data. But it's also a bit peculiar in the sense that every code is run in tiny processes and stuff, but I'll get into that a bit more later. So there's just a small example there, and I do realize that it doesn't really show very much, but I just thought I'd put it up there, just so you see how it looks like. So the first thing you might see is that the syntax looks a bit Ruby-ish, maybe. And there's a very good reason for that, because the language was invented or created by Josephsen, which he was a Ruby on Rails core developer. And he has become what you might call the benevolent dictator for life for the language. So he's been running the language quite well. But although it looks a lot like Ruby, the similarities mostly end there. It actually has a very Lisp-like macro system, which is really interesting for a language which doesn't have parentheses everywhere. And I'm actually really happy the talk yesterday, Adventures in Homoiconicity, mentioned this, because I think that talk explained it really well. And this language does a lot of the same things here. So if you look up both def module there and def, and a lot of the things in the code that you might expect to be keywords or the like, they're actually macros which are implemented in the language itself. So I think that's pretty interesting. So being a Lisp-like language, the full language is also available at compile time. So Unicode support in Elixir, it's implemented by actually reading the Unicode database files and just generating code, which is one of the better ways I've seen of doing it. But yeah, after all, Elixir isn't really, what you see up here as Elixir isn't really a lot more than just syntax and a package manager, because it actually built on some very good foundations. Elixir actually runs on the Erlang virtual machine. So it ends up inheriting a lot of the properties of the Erlang language. So I don't know how many of you are familiar with Erlang very intimately, but it's a language that's over 30 years old. It started up in telecoms, and as such, it was designed with some very interesting properties. So at the risk of looking like an Apple keynote here, I'll put three sort of main pillars of the Erlang language up on the screen here. So it's concurrency, distribution, and fault tolerance. But I mean, these are just buzzwords, but Erlang actually does some really interesting things to try to make these things a reality, and it has a really interesting model of doing it. So for the concurrency aspect, all code in Erlang runs in small processes. You could call them actors. They're probably a lot like actors, but in Erlang, they are called processes. It's very important to note that although they're called processes, these are not system processes. These are very, very lightweight processes. I think when you start a process in Erlang, you end up only taking a couple of kilobytes of memory for each process. So that's really cool, actually. So because you can run millions of these small processes at the same time in the Erlang VM, you end up getting some really interesting architectures for how you build your applications. It ends up being oriented around the usage of processes. And these processes, they communicate purely via message passing. So you have one process. It has no way to modify memory, like shared memory, except sending a message to the other process. There are, of course, exceptions to this. You can cheat a bit in some ways, but in general, the Erlang community really recommends that you don't use these, and the language itself is designed around you communicate via sending messages. So the second one, distribution. This is really cool, actually. When you send a message to another actor, the VM itself, you send a message to a process on another machine in the exact same way as you send a message to a process on the local machine. So you end up being able to put a process on another machine and then interacting with it incredibly seamlessly. And this ends up, you can build like clusters of Erlang nodes, which distribute the work, and it works really well. Some really cool things have been done doing that. And the last point, fault tolerance. So I got another slide here. So the fault tolerance is also done with help of the processes. So you have, as you can see here, the blue ones are supervisors and the green ones are workers. And what happens if one of the workers crashes? The supervisor will take care of restarting it, and the process itself, it loses all its state, but the assumption is that when a process crashes, there's usually something wrong with the state of the process. So Erlang focuses on when something wrong happens, the process crashes fast, and it gets restarted really quickly by its supervisor. So this is a really interesting way of doing it. And because of some of the, this is a really good way of doing it for many types of systems. And as you recall, I said it was originally built for making phone switches. And when you think about it, in a phone system, you have tons of people calling each other. And if one person calls a number that like triggers a glitch, or if something happens, then you generally don't want every phone that goes through that switch to disconnect. So you want that process to crash, and you want to get it restarted as soon as possible. That way, only the single user is affected by the bug. And although it was originally designed for phone systems, it ends up being useful today as well, because languages like WhatsApp, the messenger service, actually use Erlang for like sending messages, handling pretty much all its messages. So they run a lot of Erlang nodes, which handle all the incoming connections from the clients, and they route messages in Erlang. Okay, so I'm going a bit technical here, but that's because it is actually relevant for the second part of the presentation, so just bear with me. So a process runs on a scheduler, so you have millions of processes, and they have to be run in some way. They're not just magically run. So you have a scheduler that actually takes the process and starts execution of it. By default, there's one scheduler per CPU per CPU core on the machine. So you end up with pretty good parallelism there. The schedulers are also work stealing. So if one scheduler has a lot of work to do, has a long queue of processes waiting on it, then the others can come in and steal work from it, so that one doesn't get like hogged up. And another interesting thing that you generally don't see in a lot of other languages is that Erlang also limits execution time per process. So if you have one user which ends up stealing a lot of resources, then their process will will have a lot of work to do, but because the Erlang VM will actually reschedule processes after it's done a little bit of work, they'll get bumped to the back of the queue. So you end up with every process get a fair share of runtime. And as a quick aside here, this is not what I'm talking about, but the Phoenix framework, it's a web framework for Elixir, and it's really good for web development, actually. So when you think about it, a lot of the properties you get in a phone system or in like a messaging system like WhatsApp, you generally would like to have a lot of those properties in web development as well. If one client manages to crash your process, then you don't want the whole thing to go down. You want only that client to be affected. And this isolation actually turns out to be a really good idea for web as well. And also because you have, you run your code in a process, so you have linear code, you don't have any callbacks, so you have no callback hell. So it ends up being really, really easy to write web applications this way. So yeah, again, Phoenix, this is a good place to start if you're interested in this. They have some really good resources on how to get started. But yeah, back to what my talk is actually about. How do you talk to the outside from Elixir or Erlang? You have a couple of methods to do that. You have ports, and ports are pretty easily explained. That you start a process, you talk to the process with standard in, standard out. This could work for some things. If you start like Git or something from the program and you just want to like, get a git commit log or something, then that might work really well for you. But generally, like the overhead of starting a process or the overhead of communicating with a standard in, standard out, it's not really optimal for a lot of cases. So there's another option here. This one is a little bit more unique to Erlang. You have foreign nodes. So you remember I said Erlang can be distributed. You can send messages to other machines, other nodes on the network in the same way you send to a local process. You actually are able to implement a Erlang node in another language. So when you then send a process to the other node, you end up effectively like using the Erlang message passing to talk to the other external code. So this is a really cool way of doing things, but again, it might not be optimal for you if you're doing like JSON parsing or something, sending the JSON over the network to the other node, parsing and sending it back. It's not really optimal. So there's another option here. This is a bit similar to the first one in some ways, port driver. You actually end up with the code communicating via pipe still, but the code is actually in process. So you load a executable, like a library, into the process, and you communicate it via pipe. And then the last one, this is what I'm mostly talking about here. You have native implemented functions, which are shortened down to NIFs. So yeah, on the two last ones there, port drivers and NIFs, you end up loading executable code into your process. And if you've ever done any native application development, you know that if you load executable code into your process and you do anything wrong in that code, then it's really, really easy to make things go boom. So like just like a tiny pointer error or whatever you do, you can end up segfaulting the whole Erlang VM. And if you remember how I talked about the way fault tolerance is done in Erlang, that's a really bad thing. You end up not just like killing your application process, but you end up killing your whole like platform of things. So a lot of people actually compare Erlang to a bit more as an OS in this regard, where you end up running parts of your database. You remember the barrel DB talk? You can run a database in process, and if your Erlang VM process actually crashes, then you are screwed. That's inconvenient. No worries. Thanks. So yeah. Okay, so yeah, this is where Rust comes in. Rust can offer a lot of guarantees for what can happen, what can't happen. You can have a lot of safety guarantees in your code if you write it right. So I'm going to talk a bit about Rust then, because not all of you might be very familiar with it. It's a language by Mozilla, the browser company. It's compiled, uses LLVM for its code generation. It's used in a new browser engine called Servo, which they're making at the moment. It's a low-level language, so it's fast, manual memory management, no garbage collector. So I'm doing the same thing here as I did with the Elixir language. I'm just having a small example here. Yeah. So if you've ever visited the issue tracker of like a moderately sized C project, you've probably seen some enthusiastic Rust developer just posting the bucket list of Rust features that you see on the screen here, and like you should port it to Rust. But I'm not going to go into all of these, but there are a couple here that are really interesting for us in our case, because you have guaranteed memory safety. So you remember I talked about the way that native code loaded into the Erlang process can really easily mess things up and crash it. So we get guarantees for what can happen or what can't happen in Rust. And you also get efficiency bindings. So because the Erlang NIF API is a C API, that's really important for us. So I did what any like enthusiastic developer would do. I went and created my own library for it. So this is the Rustler library. So you can see here, I'm going to scroll down a bit to the README, which has some of the like major points I want to get accomplished with the project. So it's safety. The main thing with the major thing I want to accomplish is that as long as you don't write the unsafe keyword in Rust, so unsafe is sort of like a cheat method in Rust. When you write unsafe, you can do anything you want. So as long as you don't use the unsafe keyword in Rust, you should not be able to crash the Erlang VM. This sounds really ambitious, but it's actually more achievable than you might think. So an ease of use. If someone wants to create an if, it should be as easy as possible to get it done. The API should be as nice as possible and everything like that. Interoperability. So it should be really easy to decode Erlang types to Rust types and go the other way. This is a major thing as well. If it's really, really hard to convert types back and forth, then not a lot of people are going to use it. Yeah, with type composition, this goes into the same thing. It should be really easy to compose different types together. You should be able to create like a composite type, container type, and you should be able to encode and decode that really easily. And resource objects. I'm running a bit short of time, so I'm just going to skip a bit ahead. So yeah, this is just a simple example of the API. It looks really complicated. Probably, if you're not familiar with Rust, there's loads of like sigils here, but it's probably easier than you think it is. So you see in the function there are sort of two parameters. There's the environment, which represents the process, which calls the NIF from Erlang, and you have the arguments, which represents all the arguments you pass to the function. And then there are you decode a integer, like 64-bit signed integer, via the decode trait. And you see the question mark on the end there, that's the Rust error handling. And you do the same with another number, and then you return a tuple of an atom and the two numbers added together. So this is just like briefly explain. So you also need to build your NIF. The project also provides tools and utilities for actually building the Erlang NIFs. So if you include Rust code in your project, then you end up having to build it for like the VM version they're running, and also the machine architecture. So you need utilities for doing that, and as well as handling discrepancies between different platforms like Windows, Mac. We have to do a couple of things to make that work. Yeah, so a NIF is actually, there's a couple of, in a couple of cases where you want to use a NIF probably. It's in I/O. When I/O in Erlang is slow, you might want to use a NIF to speed that up. Native APIs, when there's an API that's not actually wrapped in Erlang before, you could use a NIF to expose that API. Native libraries, so if you have a library which is written in lower level language like C, I mean, if you have a C library, you need to depend on the C library being bug free, but there's not much we can do about that. And performance, if you really need fast code, then you could use a NIF to accomplish that. So a couple of things we're still working on. It's the Rust installation. Right now we don't pre-build Rust code, so if you download a library which uses a NIF, there's no pre-built binaries, so you need to have a Rust compiler on your computer to actually build it, but it's mostly automatic if you have a Rust compiler. And the NIF execution time. This comes back to the fact that processes are not allowed to run for too long in the scheduler. So if you run your native code for a long time in a process, then you end up you end up destroying like the latency guarantees of your system, and other bad things might happen. So I'm running out of time here, but I'm just going to go quickly over some of the things that are written in the project right now. So I just have to ask, has anyone of you here attempted to write a spec-compliant HTML5 parser in any language? Any hands? No? So it's not really a fun thing to do. The spec is like, I think it's up to 100 pages, and there's loads of imperative like algorithms. It's written out in pseudocode for how to handle different edge cases. This is not fun to implement in any programming language, but especially in a functional language like Elixir. If you wanted to implement the algorithm specified in the spec, it's not really easy thing to do. You have to convert them over to functional style, which would not be very fun to do. So one thing you could do is you can use a NIF to wrap HTML5 ever. And HTML5 ever is a HTML parser, which is like, it's browser grade, so it can handle, it follows the spec as closely as possible, and it can parse a lot of like the bad HTML you might see. It's part of the server project. So you remember I talked about how Rust was like developed in conjunction with the server project, so it's part of that. Yeah, and this is this HTML5 binding to Elixir is actually used by at least one very popular HTML parsing library in Elixir. So Floki uses this optionally. And then this as well. This is a JSON parser. It's a iterative parser, so you don't use recursive descent. You maintain the state separately from the call stack. It's written purely in safe Rust, and the actual parser implementation is not dependent on being in a NIF, so it's totally independent. Yeah, when testing it, it's comparable in speed to Jiffy, which is a like handwritten C parser. It does some things quicker and it does some things slower, but like in general, it's within the general area of speed of Jiffy. And another cool thing, because you have the iterative parser, you can actually exit the parser at any point in the input stream. So if you have say you get like a big JSON from a network socket, or you read like a multi-gigabyte JSON file from the disk, you can actually parse it in chunks. So you end up being able to like parse in like a couple of kilobytes at a time and get the results out from that. So you don't need to have the whole JSON file in memory. And then I'm just going to mention this as well. This is a RockDB binding built in the Rustler project, which is, I didn't make this. This is made by another company called Urbint. They seem to be using it in their infrastructure. So that's pretty cool. Yeah, if I had time, I was planning to go through how to create an if, but I'm just going to skip through that right now. I plan to, yeah, I'll try to make it really easy to do. So you just execute a command and you generate like a project quickly. So just like to finish up, a similar project, Neon for Ruby, Helix for Neon for Node.js, Helix for Ruby, Snake for Python, which we mentioned before in the first day. I actually didn't know about it before that, but it seems like a similar project. And then thank yous, Jason Orendrov, which and Sonny Scruggan, both which has contributed quite a lot to the project. And thanks for all of the small contributions from other people as well. And obviously, if you want to contribute, we are really happy to take contributions. So your name here. Yeah, and I don't know how acceptable this is, but I'm just gonna like promote my blog. So I write some interesting things, I think. So like I did one thing where I built a computer from primitive electronics parts, which I wrote a blog post about, and I also do some other cool things. There's a blog post about the project as well, so check that out if you're interested. And thanks a lot.